circuit edit focused ion beam. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Arm Sarkissian, General Manager of Engineering Sciences at EAG, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Dr. Daniel Sullivan, Account Executive at EAG Laboratories.
Well, thank you, Rena, for the introduction. And today I will be talking about FIB Circuit Edit. It's also Focused Ion Beam, CE, FIB, however you want to call it. That's what we'll be discussing today. I'll be going over what it is, when you need to use it, giving a couple of examples, and then Arm and I will be happy to answer any questions that you may have. About myself, I'm a regional sales manager here at EAG. I moved over to that position almost 2 years ago. I used to run the failure analysis group before then up in the Sunnyvale location. And I started doing FIB back in the 90s, back when I worked at LSI Logic. It's come quite a ways since then. I'm a PhD chemist from UC San Diego, and I got my undergraduate degree at Cal. Go Bears. I've been in the industry for 30 years, since 1986. So I'm happy to answer questions about FIB and anything else you might have at a later time. So today we're going to be talking about an introduction to EAG, and then what is Circuit Edit FIB, what's it used for, the sample preparations that are required, and then use considerations. We can do FIB from the front side, the back side, and what are the challenges. The picture here is just one of the very complicated FIBs that we've done. Typically FIBs aren't this complicated, but they can involve quite a number of steps, as our examples later will show you. But we can do basically surgery on your devices and allow you to check them to see if those fixes are the appropriate fixes. So EAG is a Eurofins company, and the Circuit Edit FIB is in the Engineering Sciences division. We have multiple sites all across the world, but our Circuit Edit FIB labs are here up in Northern California and down in Southern California. We have lots of other techniques at those locations and at the other locations as well. So the Engineering Sciences involves quite a number of analytical tools that we can use. We have ATE to basically go and check your devices or your wafers and see that they're working properly. We can do reliability stress testing, qualification, burn-in, ESD and latch-up testing. Of course, the Circuit Edit FIB, and then we have a full failure analysis capability as well. We also have a PCB or printed circuit board group that helps design hardware for those tests or for the AT applications. EAG was founded in 1978. We have more than 30 years experience in the electronics industry and a lot of capital equipment, over $150 million in capital. We are ISO registered, DLA, and we are also ITAR registered and automotive compliant. So we can deal with a wide variety of samples that you may have. So this is a smart chart, and Circuit Edit FIB isn't actually on the smart chart, but this is one of the famous charts that EAG came up with that we can use for our other techniques, where we can quickly look and see if the detection limits and the sample sizing are appropriate for your needs. This is something that's up on our website. It's a very handy little tool. All right, so we'll start. FIB uses gallium ions. It's a liquid gallium source that then sprays the gallium into a vacuum where the gallium is ionized, and then we direct that here in an incoming gallium beam. And this essentially is a micro sandblaster. We use this to very gently and in a very controlled manner remove material from a surface of a sample. And you can see the gallium ions come out, and the other ions that we've formed from sputtering the surface also come out, and we basically dig a trench. The ion beam is what we use here we can look at the secondary electrons or ions that come out to give us an image of the surface so we can see what we're doing as we do the cut. One of the other things we do on some of these systems is we can put in a secondary gas here to enhance the cutting or to deposit a material. So if we wanted to cut SiO2 and we want to enhance it, we could put in something like water. If we want to deposit a metal, because we want to make a connection, we can put down tungsten or platinum hexacarbonyl and put down a conductive layer. If we want to put down an insulated layer, we can use something like a TiOS or an SiO2 type of gas that we can deposit out the insulating materials, and that way we can put down insulators, conductors, and cut things. We can essentially do surgery on your devices. So as I just talked about, it's ion milling to cut traces in a semiconductor die. So if you had a device that was not operating properly, or if you want to check and see if a connection is doing the thing that it's supposed to, we can go in and cut one trace and you can retest the part and see if that trace is doing what you expect it to do. We can also do a more involved microsurgery. We can make cuts, place new traces, and this allows you to alter the circuitry and then go test that alteration and see if that's the correct alteration that you want to make instead of going and doing a respin. We're also able to do a placement of probe points onto traces. Basically, you touch down to a trace, make a metal connection, and you bring that connection up to the surface. This allows for benchtop monitoring of signals in a device while operations are done. So you can go in and check for voltage droop, check for current at certain locations. The other thing that we use the FIB for quite often is the removal or addition of metal lines to alter a resistance or a capacitance of a device like heaters or delay or clock lines. So anything that your device can be made to do by putting down some extra metal or insulator, we can do with the dual beam, or sorry, with the circuit edit FIB. All right, down here in the left hand, or in the right hand corner, sorry, where the laser beam is, this is a cut. Essentially, we've gone in, found a trace, and simply cut it away so that we can now no longer have that trace attached, and we can do tests. In this, it's the same sample, but we've gone in here and we've exposed 3 different areas. So we've gone in and we've removed the oxide above a trace. Then we've taken a metal deposition and gone and made what's called a jump, where we've connected to these 2 spots, and that part is still cut. So in this way, we can essentially detach one area on the die, attach 2 other areas that weren't previously attached, and go do the tests and see if that's what we want to do in the design. For the probe pads, we want to do bench testing. We could do 1 or we could do multiple. And in this particular case, we've gone in and we've dug a fair number of holes here. And then we've gone down and exposed the target metal underneath. And then we've gone and attached metal and come up here and made crosses. And over here on the right, you can see the final result. We have 7 probe pads now. And the reason we use a cross is the probe that we're going to use on the bench is essentially a sharp needle. And we want to come in, hit that cross, and then we don't want the needle to skid off. So we have this cross area, so we can come in and catch right in the corner, and that makes for a much better probe location. And then we can basically run IV curves or run part of the device and then check, monitor the probe pad here for voltage and current. So this is an example here on a 28 nanometer device. Now, what I'm showing you here is not the device itself, but rather the GDS2 file, which is where we plan out the operations we're going to do. And then we can essentially, with some fiducials, line up this GDS2 on top of the wafer or the die once we have it in the FIB, and we can use this essentially as a map to drive around on the surface. In this particular case, this is an aluminum top layer and 8 copper layers, so we can work on parts that have multiple layers here. And we want to basically make a cut in M2 and then connect M2 to M8. And what we've gone is we've gone in here and planned out what we want to do to show the connection and where the cuts will be made. We can then go in here and remove the aluminum layer and the M7 layer. Then down here, we can go and plot where we want to go and basically cut the M2 and then create the jump. There. So this required some planning. In the old days, back when I first started doing FIB, we simply try and find a location and we dig a very deep, very narrow hole and try and make connections. We used to call them oil wells. We would go drill an oil well. Those are not great. They don't have a super high success rate. But now, part of the reason that EAG is so good is we have some people that can go in with the GDS2 files and locate and plan out a strategy for the best chance of success to make these connections. In this case, this yellow box here, we've gone in and we removed the aluminum layer. Then in the green box, smaller inside that first box, we remove the M8. And then the smaller red box inside, we remove the M7. And then we are able to mill this very flat bottom of the square, and we can go in and we can remove the dummy layer and expose M2, but not cut it. Finally, we're able to go and coat this entire area with SiO2, so we won't get any shorting between the different exposed areas that we've created by digging down in these trenches. And then we're able to go and expose M5 and M6 to get our reference points, and then expose the M2, the target M2. And here's actually what the real edit looks like. We've driven this larger box, a smaller box, and then at the bottom of that box, we can go in and make the final cuts. So the aspect ratio isn't super high because we've been able to go and do this plan. Once we cut the M2 there, we're then able to make a metal connection and finish the entire thing. After that, if we wish, we can seal the entire thing in the SiO2 in order to basically get rid of any chances of leakage or shorts, and also protect the part so that it's able to last for a longer period of time to go through testing. All right, so this is a second case. It's like the first case, but slightly different in that this one has a 9-micron thick copper RDL layer on it. So the redistribution layer is quite thick, and this can be quite a challenge if your planning or your tool or engineer are not quite up to the job. So what we're able to do is remove this 9-micron thick copper RDL layer and then go down to the lower layers in a reasonable time frame with a high success rate. And then we can cut the M2 points that we want to do and make jumps between M2. So in order to do this, we again had to go take the GDS2 file, make a plan and a strategy to go in that would give us the highest chance of success. We're able to take this large box here and remove the RDL layer. It's about a 25 by 25 micron box, which is pretty big, but we wanted to give us a good space so we wouldn't have any interference when we want to go in and do our more delicate cuts. Then in the smaller green box in the inside, we remove M5 and dummy M4. And then over here in the red box, which is inside of that green box, we go in and cut the area free to expose the area that we actually want to look at. And then what we're able to do is we seal the entire thing with SiO2 again in order to get rid of the possibilities of shorts and leakage. And then we go in and cut the green box, and then we make our M2 cuts, and then we can seal the entire thing again with the SiO2 to reduce any chances of leakage. Now, those were front side cuts. We can also do cuts from the back side on a flip chip, for example, or on a wafer. Now, we have ways to thin that silicon down. The silicon is typically something like 750 microns. We can do some universal polishing with an ASAP tool or a tech prep tool, a variety of ways to make it thinner, but we don't have to. This is actually just an example showing you where we've done a trench that's 750 microns down to the active region from the back side. And then we've gone inside of here and done a jump and a small cut. So it can be done. We don't have to take off the 750 microns. It is a thing that reduces the time required a great deal, but it does, change the structural integrity of your die because it's so much thinner. But we can do either of those things. We have both options at EAG. Now, you may have some wafers or die that are already bumped. So these large solder balls are in the way of things. Some groups are not able to do FIB on these parts. We've done FIB on bumped wafers a number of times, provided that there is an access point, and that's why we need the GDS2 file to go in and make a strategy and find the locations that are appropriate. And we can go in here and we can make some trenches and do the cuts here and then we've gone and done some cuts and some jumps on a device that is actually already bumped. Now, this then allows you to go over to a tester and test your bumped wafer instead of having to remove the bumps, or you could actually assemble this part and do tests that way. We will cover this area here with SiO2 in order to protect it, and obviously this is a testing device. You shouldn't go put this in something that controls an airplane or something, but for the testing purposes, this is perfectly good, and we've done this a number of times. So the challenges for circuit edit FIB have always been that we need a GDS2 file for most cuts and most operations. If you've got a very simple cut on top layer metal, then quite often just some printouts or images might work. But for anything more complex, we need that GDS2 file because we drive around with it once we hook it up to our system, and that's what we use to essentially drive on the map of the device. But it's also very critical that we plan out the cuts and jumps ahead of time with a full GDS2 file so that we can get the best chance for success. Now with that, we need the layer map or the technology files as well. It's very helpful for us to have the process technology and the layer thickness information so that we can understand the timing that's going to be required, and the engineer that's doing the operations isn't having to guess at the thicknesses as they go. General information about the product, knowing the product type and what it's going to be used for, helps us considerably in increasing the yield for the FIB operation. So if we know that leakage is something that is not terribly important versus on a device where the leakage is crucial, then we may choose a different path in order to get the same operation done. Now, we do need to expose the die in packaged devices. So on a wafer or a flip chip, we do need to have access to that silicon, but on a wire bond device, we do need to access that front side. And in doing so, we need to remove the encapsulant, but we don't want to damage your bond wires most of the time. And those bond wires are gold, copper, or aluminum. And depending on which one it is, we have different decap processes. So we'll need to know that ahead of time. If you don't know, we can do some tricks with our X-ray tool and pretty much determine what it is that way, but we need to know ahead of time. For the flip chip devices, if they're heavily doped, we'll need to thin the die. If they're not heavily doped, depends on how complex the operation is, whether we should simply FIB directly or if we want to thin the device, depending on the time required and what you're going to do with the device afterwards. Now, at the end of this entire process, we can recap the parts. We have a HiSold that we can go ahead and fill in the holes and make your device covered so that it's, if you're going to do a salt spray test or something like that to it, we can protect the device that way. It's also helpful to do that when you're going to go put it back in the clamshell for the tester. And if we know that, we can actually make that top nice and smooth instead of rounded, and then it will fit in your clamshell and your testing will be simpler. Now, who needs this type of capability? The circuit edit FIB can be applied to any die, wafer, or packaged part as long as the die is exposed, and we can do the exposure here at EAG if necessary. Now, the modification of these devices in a couple of hours typically, and the more complex ones can take a couple of days, but this allows a rapid verification of your issues, and you'll be confident that the changes you're thinking of making are the correct ones before you go do a major design change or mask changes, along with a respin to make new devices and then do the tests. This saves weeks and sometimes months of time and hundreds of thousands of dollars. And we all know that one of the #1 things in semiconductors is time to market, right? If you're delayed 3 months because you have to do 2 respins, that is really a terrible event. Whereas those device changes can be checked with FIB in a matter of days, and then you do 1 respin instead of 2 or 3 respins. The experts at EAG have worked on all kinds of devices, including 7-nanometer silicon devices, as well as silicon germanium, silicon carbide, and gallium arsenide chips. Our guys have seen an awful lot of different types of samples and have planned out and carried out very successful FIB operations on a wide variety of devices, and we're happy to have them talk with you if you have a particular issue you want to address. And why would you choose EAG? I think, Aram, were you going to take over at this point, or did you want me to go through these? I think it's me.
You can keep going.
All right. So Why you would choose EAG is that our confidentiality is core to our business. We have NDAs with the vast majority of our customers, and even when we don't have an NDA, we behave as though we have an NDA, because that's our business is to do your work and to not talk about it. We're established thought leaders, and we have lots of skilled and experienced individuals here. We have a multiple disciplinary approach, and if you say need circuit edit fib and you need something else, EAG can help you with both. We own a lot of instruments. I think there's over 2,500 instruments worldwide. Now, not all those are circuit edit fib, but we have a number of circuit edit fib tools, both in Northern and Southern California. And we are ISO accredited, and we can help solve your materials problems, and we're happy to work with you.